All right, thank you so much for sharing with the partner. So these questions 4 and 5, they basically have the same answer because they're basically asking the same thing. Number 4, we're going to sort of explain these ideas a bit more informally, and then in question 5, we'll do like the actual, proof of it. Okay, so there's a couple of ideas that we want to keep in mind for number 4. And the first one is that ABC fits the definition of a dilation of triangle AMN, right? So ABC is okay, so ABC, the big triangle, is a dilation of AMN, the little triangle, by definition, right? We showed up here in question number 2 that it fits the definition of a dilation. Okay, so then now that we know that those triangles are dilations of each other, now we can apply the definition to figure out like other stuff like the scale factor, and we can also talk about properties of dilated figures, right? So one thing that we know about dilated figures is that corresponding sides are proportional. Okay, so we can say okay. And they're not just proportional to each other, but they're proportional specifically to the scale factor. And we proved that the corresponding lengths that included the center of dilation were proportional by definition, and that these other lengths, any length, is also proportional to the scale factor, but we did not specifically prove that. We took it as an assertion. Okay, so this is still an assertion, but it's something that is true. Okay, we just don't have the scope to prove it in this class. Okay, so now we want to say that MN and BC are corresponding sides. And the scale factor is 2. How did we know that the scale factor is 2? Well, because M and N were midpoints, right? So that's how we knew that because these are midpoints, the longer sides, AB, is like twice the length of AM. So all of that to get, therefore, BC is twice the length of MN, because all lengths are proportional, not just, all corresponding sides are proportional, not just the ones that included the center of dilation.